Hi, I'm Jarvis. I'm a PhD student working in Todd Murphy's lab. So far in this class, you've learned some really useful tools. You've learned about constitutive laws, Euler integration, linear differential equations, and even some linear algebra. But it turns out in the real world, there's some situations where these tools just aren't quite enough. And I want to talk to you about some of those situations today. And I want to do it by talking about some research that we actually do in the lab. So what we have here is a robotic system. System of robots driving around, and they all have strings hooked to this puppet. And what we're interested in doing is writing software that will automatically build controls for these robots. So we want the puppet to do something, and the software will tell us what the robot should do. It turns out that that's a really hard problem. Just modeling the puppet and simulating what it's going to do is really complicated, and figuring out how to control it is even worse. It's got tons of joints, but you only have a few strings hooked up to it. And as soon as it starts moving, it starts swinging, and it keeps swinging forever because there's almost no damping. And so you have to figure out how to control that swing if you want it to look like a human. Now, why would anyone want to robotically control puppets? Well, we really don't. We're more interested in just sort of general algorithm and theory development, and we use the puppets as a context for doing that research. The puppets we chose in particular because they have some really nice properties. Even though they're super complicated, it's easy to have intuition about them, and they're made up of really simple components. They also sit at just the right level of complexity. They're hard enough that you can't write down the equations by hand, but they're definitely simple enough that we have an idea of where to start. Finally, we know that there's probably a solution. We know that people can figure out how to control them, so that gives us some confidence that we're actually asking a solvable problem. So the first area I want to talk to you about where the tools you've learned in class are not quite enough has to do with nonlinear differential equations. Now in lecture 2 you learned about linear constitutive laws, but then in demo 4 you heard about nonlinear constitutive laws. And that's one source of nonlinearity in differential equations. But it turns out that even with simple components and linear constitutive laws, you can have nonlinear differential equations. Now what is a nonlinear differential equation? Well, in lecture 11 and 12 you saw this equation. W dot is equal to AW, where A is a matrix and W is your state vector. Turns out any differential equation that can be rearranged and put into this form is a linear differential equation. If it can't be put into that form, it's probably a nonlinear differential equation. Now let's take a look at this super simple thing. This is just a pendulum swinging back and forth. It's basically the simplest puppet you could possibly imagine. Turns out, if we define this as x, our state, our configuration, and we define gravity as a force pulling downwards, and L is the length of this string, this is a nonlinear differential equation. A system that simple is nonlinear. Its differential equation is given by this. X double dot is equal to negative g over L times the sine of x. And it turns out that that sign makes it so we cannot put this equation into the form of this equation. So it's nonlinear. Now why are nonlinear differential equations a problem? Well, all sorts of crazy stuff happens with nonlinear differential equations. Sometimes you have equations that have no solution or have multiple solutions. You can see crazy things like instability and chaos. Basically, they're really hard and they're not at all understood. Unfortunately, they're just a way of life. In modern research, we just deal with nonlinear differential equations. The puppets are nonlinear. You saw biomechanics in demo 4 that's nonlinear. And in the future, you're going to see us talking about the power grid. It's just how it is. The takeaway message for you in this class is if you see a nonlinear differential equation, be a little bit nervous about applying the tools you've learned to that equation. So the next thing I want to talk to you about, where what you've learned isn't quite enough, has to do with model scalability. So I talked about how the puppets are really complicated. Turns out their state dimension is greater than 100. Your differential equations, you have 100 of them. There's no way you could sit down with a pen and derive all of those. They're way too complicated. So it turns out we as researchers have to come up with tools to get the computer to automatically build the differential equations for us. Now I'm not going to go into detail how we do that. I just want to point out that as you start scaling up what you've learned in this class, suddenly you're kind of left without being able to handle it anymore, and you need tools to help. So the last thing I want to talk to you today about is some issues related to numerically approximating the solutions to differential equations. In lecture 4, we used equation 1, which is a numerical approximation to the derivative, to derive equation 2, which is Euler integration formula. You should definitely be familiar with this. Then in equation, or in lecture 5, we used equation 2 to simulate a simple system, and we actually saw that the accuracy of our approximation was a function of dt. The smaller dt was, the better our approximation. Well, it turns out you can also come up with a much better left-hand side to equation 1. You can come up with better numerical approximations to your derivatives. And if you do that, you can come up with other types of integrators that are more accurate, even at bigger time steps. Now, Python and MATLAB have all sorts of integrators that are of this form built in, but sometimes even those are not enough. So what I'm going to play here is 2 simulations of a puppet just sort of swinging in free space. The one closer to me is simulated using what we're going to talk about in a second, which is called discrete mechanics. And the other puppet, is simulated using a more classic integrator, something like Euler integration. And you can see that something really bad is starting to happen. The entire simulation starts to go unstable. And it turns out with a system like the puppet, it's almost impossible to keep that from happening. It's just so complicated that you need better integration tools. So in discrete mechanics, what we do is instead of numerically approximating derivatives, we actually numerically approximate physical principles. So in mechanical systems, the physical principle we all know is Newton's equation. Sum of the forces is equal to mass times acceleration. Now what if we had some function that could give us an approximation to A? Let's just say we have some function g. A is equal to some g that's a function of state, time, and time step. Now, we could use this g to build an approximation to Newton's law. I should say that this is probably also only approximate. So now, our approximate Newton's law is the sum of the forces is approximately equal to mass times g. Now, in discrete mechanics, what you would do is you would take this equation and you would apply it to a system and then end up deriving an equation like equation 2 that allows you to sort of map your state forward in time. And it turns out that doing things this way can give you a ton of benefits. To see those benefits, let's look at a simple system. This is called a harmonic oscillator. It's just a mass and a spring. If you perturb it a little bit, it'll just oscillate for all time. Experience tells us that in real life there would be some damping, but in simulation we can pretend there is no damping. So oscillations are going to go on forever. Now let's simulate it using the analytical solution to that and Euler integration. So here's 2 curves. They look almost identical. This is 20 seconds of simulation time. But what happens if we drive this up to 1,000 seconds? Now you see 2 curves, and the sort of straight line in the middle is the actual solution. And these red sine waves that are going up and down at a magnitude of 130 or something, that's what Euler integration has given us. That doesn't seem right. It turns out that this is what they call a conservative system. So whatever energy it starts out with, the energy is going to be constant for all time. So let's plot the energy as a function of time to see what happens. Here's 2 curves. The flat line is the analytical energy, and the red line is the Euler integration energy. Our integrator is artificially, continually adding energy to the system. That's not really good. What if you're interested in how this thing behaves over 1,000 seconds? Now what happens if we apply a discrete mechanics-based integrator to this exact same system? Here's its energy behavior. You can see it's kind of noisy and shaking around, but if you look at the exponent on the y-axis, it's 10 to the negative 11th. That means it's barely leaving the analytical value at all. We're getting tons of benefit from using this integrator. And it turns out that that's really important if you want to do things like look at satellites moving through space for 10 years, or even look at a puppet that's really sensitive. You need that kind of energy behavior. So that's what you get from discrete mechanics. Okay, so that's it I wanted to talk about today. You've learned a lot of great things in this class, and today we just highlighted 3 issues, or 3 situations where your tools aren't quite enough. We talked about nonlinear differential equations, we talked about high-order, big, complicated models, and we talked about numerical issues that come up with just using Euler integration. So hopefully in the future you'll be able to recognize some of these situations and be aware of them. So thanks for watching.